All right, let's dive in. Have you ever really stopped to wonder how a machine actually learns? We're going to pull back the curtain on the core ideas behind classical machine learning. So forget the dense textbooks for a minute and think of this as your 5-minute crash course on the real building blocks of AI. It all boils down to this one huge question. And the answer, well, it isn't magic. It's actually a pretty structured process, a kind of pipeline that takes in all this raw data at one end and spits out intelligent predictions at the other. So let's walk through that pipeline step by step. So first things first, what are we even trying to do here? What's the goal? And look, if you remember one thing, remember this. Machine learning isn't really about describing what's already happened. It is laser-focused on one thing and one thing only: predicting the future. And this quote just hits the nail on the head. A model can get a perfect score on the data it trained on, but who cares? That's kind of like acing a practice test you've already seen the answers to. The only thing that truly matters is how well it performs on brand new, totally unseen data. That is the real exam. Okay, so if our goal is prediction, what are we building with? Well, we don't just dump a giant messy pile of raw data into the machine. No way. We have to be architects here, carefully pulling out the most important characteristics, the things we call features. These are the real high-quality ingredients for learning. Right? So what are features? They're basically how we translate the messy real world into a language a computer can actually work with. Think about it. If you're describing a car, you don't list every single atom, right? You use features, like its color, its horsepower, its number of doors. The better your features are, the easier it is for the machine to see the patterns. It's a game changer. Okay, so we've got our goal and we've got our ingredients, our features. Now we need the brain, the model that's actually going to take those features and make a decision. And here's the cool part. There isn't just one type of brain. There are a bunch, and they all have their own unique way of thinking. So the foundation for a lot of these brains is something called Bayesian theory. It's just a really smart way to make the best possible decision when you're not 100% sure about things. It doesn't just ask what's most likely, it also asks what's the cost of being wrong. Think about a medical diagnosis. The cost of missing a disease is way, way higher than a false alarm. Bayesian logic lets a model make that kind of risk-aware, intelligent choice. Now let's talk about neural networks. The very first one, the perceptron, was pretty basic. It could only draw a straight line to separate different groups of data. But then came the game changer, the Multi-Layer Perceptron, or MLP. By adding just one or more hidden layers of neurons, it could suddenly draw all sorts of complex curvy lines. This made it a universal approximator, which is a fancy way of saying it's powerful enough to learn almost any pattern you throw at it. Huge difference. Then you've got the decision tree, and this one might be the most intuitive of all. Seriously, just think of it like a game of 20 questions. The model just asks a series of simple yes or no questions about the features. Is this value bigger than 10, or is the color red? And it just follows the branches down the tree until it lands on a final answer. Super simple, super powerful, and really easy to see what it's doing. So we've picked our model. Now comes maybe the most important part of all: training. How do we teach this thing to find real, genuine patterns without it just memorizing the answers? How do we make sure it doesn't cheat on the test? It's this classic balancing act. The best analogy is a student studying for an exam. Underfitting is like not studying at all. You fail to practice questions, and you failed a final. Overfitting, on the other hand, is like memorizing every single word in the textbook, including the typos. You'll ace the practice questions, but the second the real exam asks a question in a slightly new way, you're totally lost. Our goal is to find that sweet spot right in the middle. So how do we stop the model from cheating? We use this really clever technique called nested cross-validation. The main idea is simple. We take a piece of our data, lock it in a vault, and call it the final exam. The model can be tuned and trained on everything else, but it never, ever gets to peek at that final test set until the very end. This is how we guarantee that the score we get is an honest, reliable measure of how it'll do out in the real world. All right, the model is trained, it's ready to go. But is it any good? Is it an A+ student? Or is it barely passing? It's time to give it a report card. And for that, we need some specific ways to measure its performance. The starting point for all of this is the confusion matrix. It looks a little technical, but it's simple. It tells us not just if the model was right or wrong, but how. Did it correctly identify a positive case? Great, that's a true positive. Did it miss one completely? Uh-oh, that's a false negative. This little grid gives us a surprisingly deep look at a model's real strengths and weaknesses. Now, if you take that matrix, you can build what's called an ROC curve. Just think of this as a graph that shows how confident your model is. A really good model has a curve that shoots up and to the left, which means it's finding lots of the right stuff without making too many silly mistakes. And that diagonal line, that's a model that's just guessing. It's literally no better than flipping a coin. And if you want to boil that entire beautiful curve down into a single simple score, that's the AUC, the area under the curve. It gives us one number, from 0 to 1. A 0.5 is basically random guessing. A 1.0 is absolute perfection. So it's pretty simple. The closer your AUC is to 1, the better your model is, period. So we have our one trained and graded model. But what if a single expert, even a really good one, just isn't enough? This brings us to the final, really cool concept in classical machine learning. Sometimes a whole committee is way better than a single genius. And this is all based on a powerful idea called the no free lunch theorem. All it really means is that there's no single magic bullet model that's the best for every single problem. So, if no one expert is guaranteed to be perfect, why not build a whole team and combine all of their strengths? And there are two really popular ways to do this. The first is called bagging. That's kind of like asking a bunch of experts the same question, but giving each of them a slightly different briefing, then you just take a majority vote. The other way is boosting. This is more like building a team, one by one, where the second expert is specifically trained to fix the first one's mistakes, the third one fixes the second's, and so on. In both cases, you end up with a team that's way smarter and more reliable than any single member. So that leaves us with a pretty fascinating thought to end on, doesn't it? We went from setting a goal to picking features to training and grading a single model. But maybe the peak of this whole process suggests that true intelligence doesn't come from one perfect, isolated brain, but from the collaboration of many. And that's a lesson that might just apply to more than just machines.